Okay, now assuming that U-boot has done its work and has loaded the kernel into memory, right? What does it do? It basically jumps to the start of the kernel, meaning that it performs a branch instruction which takes it to the point, the starting address corresponding to the kernel, right? Now this is the first thing that the kernel code needs to do is, it needs to check if you are working with a compressed or uncompressed kernel. The VM Linux that we were talking about in all our examples is uncompressed, but in practice usually we work with compressed kernels because we don't want too much disk space to be used for the kernel image, and more importantly we want it to load fast into memory. Okay, so if it is compressed, it needs to extract the kernel. Now it comes to two important things, which is basically setting up what are called the page tables and enabling the MMU. We'll talk a little bit more about this in a moment, but basically this is where the entire sort of virtual memory behavior or implementation of the system comes into play, right? So from this point onwards, virtual addresses are in use. Up to this point, it was pretty much dealing directly with physical addresses for the most part. Very limited use of virtual addresses, if at all anything is there. Now once that's done, you essentially need to set up things that are specific to the architecture. Check the command line to find out where the console should be, where should you be printing messages, are there any specific requirements on clocks, and so on, right? Memory management is initialized over here, interrupts are set up. Okay, after that you basically get to the point where you are basically going to parse the device tree, right? So you can see that the device tree is also fairly early in the boot process, right? So far I just have basic memory management and interrupts, and then I straight away want to go look at the device tree, because only after I have parsed it, created this tree and extract the resources, do I have all that compatible information which allows me to probe for drivers. Okay, and here I can basically probe the drivers, which means run all the initialization routines and so on, check the compatible drivers, allocate resources as required, right? At this point at least most of the hardware is now up and functioning, which means that I move on to the interactivity, right? At this point I will basically mount the root file system. That's basically what we typically refer to as the slash file system. So there is a /bin, /lib, /user, all of those are somewhere on disk, right? They need to get mounted into an appropriate part of the memory space of the system, right? In other words, the kernel needs to know where to find each of these different files. That is also where it executes the very first program in a Linux system, the init program, right? And at that point you are entering user space, meaning that from there onwards the init program's job is to take over and say, okay, now it will allow you to basically start any other programs that you want, right? So by this point everything about the kernel is already in place. The drivers have been set up, the memory management is done, any resource management is done, the schedulers, the time, the ability to sort of multitask between different processes is all active over here, which means that I can go into user space and start running the actual code. So there are a number of different functions that sort of do play an important role in this, right? Just some names are mentioned over here, but I don't want to go into the details of these because this is stuff where you would actually need to go into the kernel and start understanding how these different functions are implemented. Okay, well worth it in order to understand how exactly the system works, but out of the scope of what we are looking at over here. So the device tree plays an important role in this entire boot flow, right? It essentially, as we can see over here, only after I have got to the device tree can I get to the point where I can probe for drivers. So the U-boot basically takes care of loading the device tree blob, right, the DTB, the device tree blob, into RAM at a known address, right. So now you sort of see why exactly we were compiling the DTS, the device tree specification, into a device tree blob, because it is directly loaded into memory. It's not like the kernel can actually, or the kernel would prefer not to have to parse through and read some complicated data structures over there. Ideally, if we can have a very fixed size structure which is easy to parse and easy to validate, that would be much simpler to use. That is essentially what a DTB is, the device tree blob. U-boot loads it at a known address. That address is then passed into the kernel, right, again through some standard approaches, which means that the kernel can basically access that DTB and parse it, at a fairly early stage, right. So in the context of ARM, there is a specific register into which the DTB address is actually written, and that is how that information is passed to the kernel, right. But there could be other approaches that you could find in other kinds of architectures as well, right. All that matters is that both U-boot and the kernel agree on where the DTB or how that information about the DTB is going to pass from one to the other. Remember that both are under user control to some extent, which means that if you do want to change it, it's possible provided you change both U-boot as well as the kernel itself. So the kernel parses the DTB, and it does this before fully initializing the memory management unit, because it's possible that the DTB itself could have some information relating to the MMU. It's used for all further processing regarding drivers, right, resource allocation, driver binding and so on. And once all that is done, in general on ARM processors you can access the device tree through this virtual file /proc/device tree, right. So you can actually boot into an ARM system and look for this particular file, and that should give you information about what device tree was the system started with. As we have discussed multiple times before, why do we even use a device tree? So that the same kernel binary can boot on different hardware, right. Let's say that I have a different set of peripherals, I just have to change the device tree blob, put that in place, U-boot then loads that, and without necessarily recompiling the kernel, right, my kernel will then be able to probe the appropriate drivers and find out what are the required peripherals that are attached. So the final part of the boot process, right, we are almost ready to enter user space, is what's called the init system, right. And as I said, the kernel itself is an ELF program, right. It's a program that's running on your CPU. What it does is to execute another special program which is usually called /sbin/init, and this starts user space. We call it user space because that's essentially the part of the overall computer experience that is interacting with the user. Now in all the examples that we followed so far on Renode, we used something called BusyBox, right. So BusyBox is a very simple minimal footprint init system, right. It provides you with the experience of almost having a complete Linux system, but if you look carefully at how BusyBox works, you will realize that all the commands that are there, right, starting from ls and cd and various other things, the shell itself, are actually just linked to one particular executable program, right. So what it does is it basically compiles everything into one single program, right, which is very lightweight but has certain limitations in what it can do, right. It typically has a single threaded startup. It's meant primarily for use in embedded systems, right. Now a full blown Linux system, right, for example the Raspberry Pi, right, or for that matter your laptop, right, or desktop which is running Linux, is not going to use BusyBox, okay. They will use, usually the most common one these days is something called systemd, but there are a few other initialization routines also that are available, right. Systemd is capable of doing a lot more. It can basically manage multiple services that are running in the background. It comes more from the desktop and server world, which means that it's more complex, but it's also more full featured, meaning that there are a lot of features including the ability to actually put up a complete graphic desktop, interact with it, files, managing multiple background tasks and so on, okay. So these are the options that are available. As we said, BusyBox is what we have used for most of our purposes, and most embedded systems tend to prefer something lightweight like this, okay. So of course the choice depends on the system complexity and your requirements. If you are working with something at the level of complexity of a Raspberry Pi, BusyBox may not be good enough for you. You probably want including the graphical user interface and so on, at which point either systemd or one of the other init routines that are available is probably more likely.